So last Thursday, we began looking at polynomials, and we saw how to add the polynomials and then multiply. We want also to look at polynomials today and then tomorrow. I think by Thursday we'll be done with the polynomials, and then we'll go to something else. Today I want us to look at how to divide polynomials using Euclidean division. Earlier on, we had looked at Euclidean division using integers. And so we'll just be using the same knowledge this time again with the polynomials. So once you know how to deal with the integers, that knowledge that we use while dealing with the normal integers is the same knowledge we use with the polynomials, and we saw how we were able to add and multiply polynomials just the same way we do with the integers. So I'll begin by looking at Euclidean division, and we know what Euclidean division is. Last time, when we were looking at integers, for instance, supposing you have the integer 10, and you have the integer, let me say 3, and you are saying that 3 goes into 10 3 times, and the remainder is 1. This is what we call a Euclidean division, where you have the quotient. Of course, you have the divisor, the number that you're using to divide. Then you have the result, which we then call the quotient, and then we have the remainder. So when you have a number, you can write that. We have two numbers, and you can express one of the number in terms of the other. For instance, when you talk of 8, and we say 2 goes into, no, 3 goes, let me use 5. 5 goes into 8 once. So this becomes the quotient. And then what is the remainder? So that is what we call Euclidean division. And that is what we want to do with the polynomials this time. We have two polynomials, and you want to write one polynomial, to divide one polynomial into the other and get the quotient and then the remainder. Now, but very interesting are polynomials where division gives us 0 remainder. That is what is very interesting to us, and we shall look at such polynomials. Now, so definition of Euclidean division by polynomials is what I've just said. That supposing you're given two polynomials, f of x and g of x, and supposing that g of x is not equal to 0, and you want to divide g of x into f of x. Now, so if you divide this g of x into f of x, you find the quotient and then the remainder. This then what we call Euclidean division by polynomials. So if you can write one, you can divide one polynomial in the other, and then you get the quotient and get the remainder. That's what we're talking about. Now, last time we defined what the degree of a polynomial is, and we said that was the highest power of that polynomial. For instance, if you have f of x is equals to 2x raised to 5 plus 3x raised to 2 plus 9, then the highest power of x is 5, and this is the degree. That is the degree. Now, but what I'm interested in is that when do you stop dividing? When do you stop dividing this into this? So once you've gotten the quotient and then the remainder, you only stop if the degree of the remainder is smaller than the degree of the divisor. So if the degree of the remainder is smaller or is less than the degree of the divisor, then you stop the division. Now, in so doing, when you're dividing a polynomial into the other, the remainder and the quotient will be unique. What that means is that you cannot get two different quotients. It cannot give you two different quotients. So every time you divide, you get the same quotient, and the remainder will be the same. So, not give us different results. Now, so let's go through the steps of doing division. We want to divide a polynomial into the other. Now, so supposing I have this polynomial f of x, and this is 4x raised to 5 plus 3x minus 10. And another polynomial, let me say 2x raised to 3 plus 7, for instance. Now, I want to divide this into that and find out how many times does it go there and what is the remainder. That's what I want to do. So the first thing I do, I've said, for me to divide this into this, I'll identify the leading terms. Identify the leading terms and then divide the leading term of this divisor into this leading term. So this is what I'm calling the leading term. These are the leading terms. So I'll ask myself, how many times does this go here? That's what I'm saying. As I'm saying that identify the leading terms and then divide the leading terms. So you ask yourself, how many times does this go here? That is the answer. We shall just be using long division, and we'll be seeing how we'll be doing that. And then we ask ourselves, how many times does this one go here? Then, as you normally do, supposing this is 2x plus 7, and that is 4x raised to 5 plus 3x minus 10. And supposing you say that it goes there 2x squared times. Supposing you say it goes there those 2 times. So you will now multiply this and this, the whole of that, and write what you get here. Just the same way we do for the long division, then subtract the results. Get what is there, and then bring this one down again. Then again, ask yourself, what about this leading term? How many times does it go here? Then again, you write the result here, multiply this and that, and put it, then subtract. So those are the steps I was explaining there. So you can see the first one I was identify the leading term, then find out how many times the leading term of the divisor goes into that of the numerator. And then you will multiply and subtract the way down. Then you repeat the steps until the remainder is 0, or until the degree of the remainder is less than that of g of x. Now, so I'll take you through examples, but before that, you need to know why this is important, why polynomial division is important. And in cryptography, we'll be applying, of course, the knowledge of polynomials in several parts, like even in the RSA, we'll be applying that, even in elliptic curves.
Even in KCG and lookup.
Yes.
Kwanza
Yes.
hiyo ya roots of the polynomial inatumika sana.
Yes, there are so many areas we'll be applying that, and so we need to know polynomials which are reducible, the ones we can factorize, and the lessons we'll be factorizing polynomials. And so for you to factorize again, you need to know how to divide, so that you know how many times does it go there, and then be able to factorize. Now let me just look at the first example. I want to divide this polynomial into this. And you can see I'm talking about integers. This is a polynomial where the coefficients, these coefficients are integers. So this is how we write it. The coefficients, it means the coefficients are integers. Now, after this, we shall look at where the coefficients are integers mod n or mod p, and we shall look at that example again, where the coefficients are integers mod p. But this time we just talk about coefficients being integers. So once you know how to do this, then it will be easier to do when the coefficients are integers mod p. Now, so I want to divide x minus 2 into x cubed minus 2x squared plus 4x minus 8. So this is how we do it. This is how we've been doing it. This is just x. So I said you then ask yourself, this leading term, the leading term, this x, how many times does it go here? Then you find it goes the x squared times. X squared times. Now this x squared multiplied by the whole of this gives you x cubed, and then this times that gives you minus 2x squared. Then subtract. When you subtract this from this, you have 0. When you subtract this from that, you have another 0. Then bring this one down. 4x minus 8. Then ask yourself again, this leading term, x, how many times does it go into 4x? Just divide. This is just normal division. Goes there 4 times. It's positive. So this 4 times the entire polynomial, the entire of this polynomial would be 4x minus 8. Then again subtract, you have a 0. So that's how you do it. In mine you can see the sign is a bit different. I've already multiplied the entire thing by minus. Because what you're supposed to do, you're supposed to, after multiplying this by that, you get x cubed minus 2x squared. Then subtract the lower result from the upper result. That's how we do it when we're doing long division. But this minus is the one I've just multiplied through. So this minus times this minus, this is positive there. And this minus times this positive, this minus. And then I add this. Then I just add. That's how I was doing mine, just to make my work easier. But you can see how I've divided that very easily. And again, I'll do another example to make it easier for us. So you can see that our polynomial here went into this polynomial this number of times, and the remainder was 0. So that is why I was saying, once you know how to multiply, then you can factorize. So what this means, of course, is that the polynomial that we have inside can be written in terms of this other polynomial. Because you can now write it as x minus 2 multiplied by that power, x squared plus 4. Now, if this can be factorized, you can still factorize it. If it can be factorized, you can still factorize it. We shall see, although it can be factorized, but not in zx. This one can be factorized in the complex numbers, where the coefficients are complex numbers, and not where the coefficients are z of x, where the integers. So where the integers, it remains like this. It remains like this. But this was not the mission. The mission for this lesson was just to learn how to divide. Then we shall have a day for just factorizing and see how to factorize when the coefficients are integers, when the coefficients are integers mod n, when the coefficients are complex numbers, or when the coefficients are rational numbers. Now, so what have we seen? We've seen that this polynomial divided by this gives us the quotient, and the remainder is 0. So our Euclidean algorithm, what does it say? The Euclidean algorithm says that this polynomial, how do we write it in terms of Euclidean algorithm? So this is the same as x minus 2 multiplied by x squared plus 4, and the remainder is 0. So that's how we normally write in terms of Euclidean algorithm. So where you have to note how many times it goes there and what is the remainder. Now let's look at another example again. Another example. I want to divide x squared plus 4x minus 2 into x raised to 5, 0x raised to 4, 0x raised to 3. No. X raised to 3 is 2x cubed. So this is, and then 0, the space is, let me use this space, it appears. So I want to divide this x raised to 4 minus 2 into x raised to 5. Then there is a 0x raised to 4. Then there is a 2x cubed. There is a 0x raised to 2, 0x raised to 1, then minus 7. So I'm spacing where there's a 0, I'm spacing so that I don't congest my working. Now, as we've just done before, we ask ourselves this leading term. This leading term here, how many times does it go into the leading term here? So it's just x raised to 5 divided by x raised to 2, and the law of indices says that you subtract the powers. So it goes there x raised to 3 times. So x raised to 3 times. Those are the number of times it goes there. Then you multiply that x raised to 3 times the entire polynomial. So when you do that, and when you are multiplying, of course, the law of indices says that if you have this times x raised to m, the law says you add the powers. So n plus m is the result you get. So you add the powers. So I'm now multiplying this x raised to 3 times the entire that. So x raised to 3 times x raised to 2. X raised to 2 times x raised to 3. You add the powers and you get x raised to 5. Then x raised to 3 times 4x, you get 4x raised to 4. And then x raised to 3 times minus 2, you get minus 2x raised to 3. Then subtract. This from that gives you 0. There's a 0 here. So this from that 0, you get negative 4x raised to 4. Then this from that, you have 4x raised to 3. I hope you've seen what has happened here. Because what I did was just, you at the upper part, I have 2x raised to 3. Then I'm subtracting minus 2x raised to 3 again. So this minus and that minus becomes positive. And so I have 2x raised to 3 plus 2x raised to 3, which is 2x
But I think,
raised to 3. Yes?
Doctor, but I think
Yes.
4, the part where 4 penye hiyo plus 4x, when
Yes.
you multiply na 3x cubed, 4x inafaa kuwa 4, see you add the powers, inafaa kuwa 4x power 3 hapo chini, hapo kwa negative 4x cubed.
This part. Which part are you referring to?
Okay. Hii part ya hiyo negative 5x.
Negative 5x.
Hapo kwa division. Yeah, e negative 5x minus 4x raised to 4 plus 2x raised to power 3.
Okay, let me just see where you are reading.
Let me show you.
We have this line 1, line 1, you have line 2, and then you have line 3. Which one are you referring to?
Let me show. Let me highlight it. Line 1.
Line 1, eh?
This line 2 on the
This
division
one,
part.
eh? This one.
Yeah.
Can you see what I'm writing?
That plus 4.
I have x raised to 5, then plus 4, x raised to 4. Then is it this one you are referring to?
Let me see. Yeah.
This one, yeah?
Yeah.
Okay, let's multiply again. Let's just multiply again. This by this, you add the powers. So you get x raised to 5.
Yeah.
Then this is x raised to 3 times this. What you have is 4x raised to 1 times this is x raised to 3. So when you multiply, you add a 1 plus 3, which is 4. And so you have 4x raised to 4.
Okay. I've not understood it.
You add 1 plus 3. And then x raised to 3 times negative 2, you get negative 2x raised to 3 because negative 2 has an x raised to 0. Then times x raised to 3. So when you add the powers, you have x raised to 3. 0 plus 3 gives you 3. Okay, so after multiplying, you are now subtracting. You just subtract direct. You don't need to always begin on the right side. These are not integers. You can begin from anywhere. So long as you subtracting only like terms. You don't subtract unlike terms. Only like terms. So the x raised to 5, its like term is this. So these are like terms. You subtract this, the lower one from the upper one, you get 0. Then x raised to 4, its like term is 0. Because this is 0, 0x raised to 4. So when you subtract, you have negative 4x raised to 4. Then this one also is a like term. These ones are like terms. So again, when you subtract, you have 4x raised to 3. You can now bring this negative 7 down. Then bring that negative 7 down. Let me just clear this space. Okay, after bringing that negative 7 down, again you ask yourself, how many times does this leading term, x squared, go into negative 4x raised to 4? So it's just easy. Or you have 4, negative 4, x raised to 4, and you're dividing with x raised to 2. This will be the same as negative 4x. You subtract the powers, and you have 2. So this is the same as negative 4x raised to 2. Negative 4x raised to 2. Now, this negative 4x raised to 2 multiplied by the entire polynomial here. So the first part, just clear that. So the first part, when you multiply, you have negative 4x raised to 4. When you multiply that, and then we have negative 16x raised to 3. And then we have positive 8. Oh, there's no need of bringing this 7 down. We have not reached a point of bringing it down because I'm not seeing where we're going to involve it. Now, this one times that, it is plus 8 x raised to 2. Then again subtract. only like terms. So we subtract this from that, you subtract this, you get 0. When you subtract this, what was this? This was 16. Eh? When you subtract, you get 20. Get 20x raised to 3. And this one is like term is 0. It's like term here is 0. When you subtract this from 0, you have negative 8x squared. Okay. It has not reached a point of bringing that down. Again, ask yourself, this leading term, which is x squared, how many times does it go into this leading term? You can remove the 0. It's not useful now. So how many times does x squared go here? Goes there 20x. 20x, you just divide, just 20x cubed divided by x squared. And you subtract the powers. So 20x times x squared, that gives you 20x cubed. Then 20x times, this was 4x. This is 4x. So 20x times 4x, that gives us 80. 80x squared. Then 20x times negative 2 gives you negative 40x. Negative 40x subtract. When you subtract this, you get 0. When you subtract this, you get 88, negative. Negative 88x squared. And this was what? This was 40, negative 40x. Negative 40x, and the x, the like term is 0. So 40x, negative 40x from 0, you get positive. Positive 40x. Positive 40x. So this is a time now to bring, is a time I think to bring this, let's see whether it's time to bring this one down. I think it's time now bring 7 down. But because of space, I now use what I had already done to just explain that working. But I wanted you to see what is happening so that when you go through my working, it becomes easy for you to follow. So I just wanted, first of all, to show you what I was doing. So you can see I was leaving space just where I needed an x, where there's a 0x, for instance, I leave as a space there because it may take, you can see sometimes it takes long before you bring 7 down. So you need to have created enough space for that 7 so that you don't have your work squeezed together. Now, so this is my x raised to 5. Then there's an x raised to 4 here. You can, if you want, you can say that. If you want, you can say that. And then if you want also, you can say 0x squared. And if you want, you can say x 0x. Because they are not there, so you can replace them by zeros. There's no problem. If you want, you can just do that. So again, what I said was, how many times does this go here? So you just divide it. X raised to 5 over x squared will be the same as x. 5 minus 2, which is x3. That's what I write. Now this x raised to 3, multiplied by the entire that, you would have x squared, you would have x raised to 5. Then this one you have 12, no, x raised to 4, and 4x raised to 4. And then with this, you would have negative 2x cubed. Then remember, you're subtracting the lower result. subtracting this from this. So it's subtracting this. So you can see mine already has that minus. What I did, I just multiply this minus inside. When you multiply inside, this is what you get. Multiply inside, this is what you get. And multiply it inside, this is what you get. So that when you are going through my working, you should be able to understand what I did. What I did is you know there's a minus here. You're supposed to subtract what is down from what is up. But that minus I've already taken it inside the bracket. I've already used it. That's why you see some signs, there are different signs from what you expect. Now, once you do the way I did, when you take that minus inside the way I did, you just now add the results. Just now add that, get 0, add this to this, get negative that, then add that to that, you have 4. And then, if this would have been something different from 0, we'll have brought it down. But since it is 0, so we don't bring it down. So ask ourselves, how many times does this x squared go into this? So again, it's just normal division. This would be negative 4 x raised to 2. And now this multiplied by the entire that. And again, I want to show you how I took my minus inside. Because the result that I get, I'm supposed to subtract it from this. So normally what we do, we normally say subtract, then you write the result down. So this negative 4x squared times that gives you negative 4x raised to 4. Then this negative 4x squared times that gives you negative 16x raised to 3. And then this negative 4x squared times that gives you positive 8x squared. So when you take this minus now inside, you get this, the first one will be positive, the way it is here. And the second one will be positive again. And the third one will be negative. So that when you do that, it means that now you just add the results. You don't need to subtract, because we've already taken care of that minus sign. We've already taken care of that. Now we just add this and that gives you 0. This and that gives you 20. Then this x8 plus this 0 here gives you this. Now, against that time, you see, I'm not concerned about these other terms. I'm only concerned about the first terms. Ask myself, how many times does this first term go into this first term? So it will be 20x cubed divided by x squared. And this will be 20x. That's what I write. Then after getting how many times it goes there, I multiply the entire result, this 20x times the entire polynomial. So 20x times that gives me 20x cubed. It will be 20x cubed. And then 20x times that will be 80x squared, 8x squared. And then 20x times that gives me negative 40x. Now this result, I'm supposed to subtract it from this. So then this is what I'm supposed to have written, minus. So when I write that, this minus just distribute it inside. Distribute it inside, and I have this, have that, and I have that. Then add the results. This gives me 0. This gives me negative 8x squared, and then 80x, and then I bring that one down. And so on. So that's how you do this. When you do that, you can find that what we are left with, which is 392x minus 188, cannot be divided by this divisor. Cannot be divided by this because its degree. The degree is 1. This degree is 2. So this one is bigger. It's bigger than this. It cannot go here. This cannot divide this. This is smaller. So therefore, this becomes the remainder. So what this therefore means is that this divisor goes into our polynomial f of x this number of times, and the remainder is this. That's what it means. So that is the remainder. You cannot force that one to go. It cannot divide it. It's a smaller polynomial. It cannot be divided by a larger polynomial. And you know, the issue of the remainders are very important to us. Those mod. So the remainder, that's, in fact, that's what we call, that's how we call it. Okay, I think there's something I'm missing here. I was compiling this, I think it came out. Huh? Because I'm seeing, but I'll just explain what I wanted. But you can see this part here has something missing. This part has something missing. Now, so suppose we want to divide mod something. That's what I wanted to do. I don't know that, yeah, okay, it's down here. It's down here. When I was compiling, I think I did compile it properly. But I wanted it to be down there. I wanted it to be down there so that I finish with this one first. Now, so that's how we do polynomials. And of course, the next part, I'll now be showing you how do we divide it in when the coefficients are integers mod p or mod n. But before that, I came up with, I wrote a Rust code that can assist us do these polynomials, divide these polynomials, so that when you are dealing with a very huge polynomial, this kind of division will take a very long time. So then you want some code that can assist you do that very fast. And so that is what I want to share so that we look at the code. Now, so this is my code. The main function is here. This is the main function. And this is where I enter the dividend, the one that I want to divide. The one I want to divide is what I call the dividend. And then the divisor. So if the dividend is x raised to 5 plus 2x cubed minus 7, then what you enter, you begin by the coefficient of, you see it goes up to x raised to 5. So x raised to 5, the coefficient is 1. What about the coefficient of x raised to 4? You must put it there, is 0. What about the coefficient? Because it's going up to a constant. It's going up to the constant. So you begin by going down. So this is x raised to 5. So the fifth term, the coefficient is 1. The fourth term, when x is raised to 4, the coefficient is 0. The third term, when x is raised to 3, you can see it's there. The coefficient is 2. The second term, when x is raised to 2, is not there, so it's 0. Then when x is raised to 1, is not there, so it's 0. So when there's no x, you have -7. So that's how you enter your values in vector form. Let's come to the dividend. The divisor. The divisor begins with x square. So this is the second term. No, not the second term. The term when x is raised, well, how many terms are these? 1, 2, 3. The third term, when x is raised to 2, the coefficient is 1. Then when x is raised to 1, the coefficient is 4. When there is no x, the coefficient is -2. So that's how you enter them. You enter. So when you begin with this, it will know that it's x raised to 2. It will know that because this is where the last term, the constant is. So it counts from the constant. This is a constant, then x raised to 1, then x raised to 2. So it again begins from here. This is a constant, x raised to 1, x raised to 2, x raised to 3, x raised to 4, then x raised to 5. So it's able to know that this polynomial is x raised to 5 plus 2, x raised to 3, then the others are 0, then -7. It's able to tell because of this arrangement. Now, so I want to know what the quotient is. So the program is supposed to print the quotient, then it's also supposed to print for me the remainder. So I just tell it cargo run. Let's see what tells me what the quotient is. Okay. So again, the same arrangement as here. The same arrangement for the quotient. The same arrangement. So this is the constant term. Then when x is raised to 1, x is raised to 2, then x raised to 3. The same arrangement as we arranged in the main function. So the main function, you can see the constant term was on the right. So this is the constant term, x raised to 1, x raised to 2, then x raised to 3. Then what about the remainder? This is the constant term, then x raised to 1. And that's what we got. That's what we got when we did our long division. I think same polynomial. I think it's a same polynomial. Now, so this polynomial, I think you can just this code. I've added my notes here, so you'll try and see if you can customize it to do more things than what it's doing here. But look at how it's calculating the remainder at this point. This is what I had already explained. That to get the remainder, first of all, it will take the leading term and then multiply the divisor. For every I, it says for I in the range of 0 and the divisor. For I in that range. So I between 0 and the divisor. That means elements between that. So that's how it's getting the remainder. So subtract, and then there's a minus here. There's a minus here. There's a minus here. So what you get as the remainder is this result, then subtracted from the dividend. That's what you get as the remainder. Okay, so this code is here, so I think you can You will try and see if it can run in your Rust. Try and rewrite it. But of course, you can also get it from my GitHub. It's over there. Now, what about if the coefficients are integers mod n? That's what I want us to look at. When the coefficients are integers mod n, that's what I want us to look at. But before that, I showed you that what I'm showing here is that after that division, we can always factorize. We can always factorize the polynomial. For instance, after discovering that x raised minus 1 divides here, because that was our b, after discovering that this one divides this, you can factor this and find these factors. You can factor once, then what to normally do for us to factorize, and I'll be showing you that you divide this first polynomial into this one first. These are cubic equation. So when you divide this into that, you come up with a quadratic equation, which you can easily factorize. Come up with a quadratic equation. Now, how do we divide mod n? How do we divide mod n? For you to divide mod n, you begin by doing what you just done. You first of all divide z in zn, in zx. First of all, divide in zx. The result that we get, reduce it mod n. The result that you get, reduce it mod n. So you first of all divide the way you've done. And the result that you get is what you reduce mod n. That becomes easier when you do it that way. It becomes very easy, and I'll show you with some example. Of course, that is what I've written in my notes here. Those steps I've just written in my notes here. Now, I have this to use as an example of this polynomial. I want to divide it by this. First of all, in z of x. Second, I want to do it in z of 5, mod 5, and then z mod 6, and see the result. But this is the main thing. This is the main thing. First, once you do it this way, the answer that you get, the quotient that you get, and the remainder that you get, reduce the mod 5, and you have the answer here. And again, this quotient and this remainder, reduce the mod 6, and you have the answer here. So it becomes very easy. The only thing you need to do is, first of all, do it here properly. Once you are done properly, then you just reduce mod 5 and reduce mod 6, the way we've always done when you are dealing with this modular arithmetic. Now, we had already done this example. We had already done this example in z of x. We had already done it in z of x. We had already divided this in that. So this is what we get as the quotient. And this is what we get as the remainder in z of x. So if we want the answer in z of 5, we want the quotient, just take this quotient. So in z of 5, z mod 5, just take now this quotient and reduce it. So the quotient will now be, this is negative 4x squared, negative 12x, negative 58. We are doing this mod 5. So negative 4 mod 5 will be 1. So you just add 5 to negative 4, and you get a positive 1. And then what about negative 12 mod 5? So you add 5 once, you get negative 7. You add until you get a positive number. So 1 should be -7, plus another 5 would be -2, plus another 5 would be 3. So you know what we are doing here, of course. What we are doing here, we are writing the remainder. What you will have done is you would have asked yourself how many times 5 goes in -12, what's the remainder? And 5 goes there -3 times. -3 times 5 will be -15. When you subtract these two, you get 3. That's what I've just written here. So instead of doing that, we normally just add and add and add until you get a positive number. But of course, we have to remember that what we are writing is the remainder, and this is how one will have gotten it. The remainder is 3. What about -58? You would add 5. If you add 5 10 times, that would be 50. If you add 5 12 times, that would be 60. So the remainder will be 2. The remainder will be 2. If you add 5, because if you add 5 10 times, it will be -50. It will be 50 added to -58. So that leaves you the -8. Then you add another 5, you have -3. Then you add another 5, you have a 2. So this is the quotient mod 5 in Z5. What about the remainder? When you take this remainder and divide by 5 and not the remainder, then it becomes easier to divide than to add. It becomes easier to divide. Now, how do we normally do this actually? We have -256. When you divide this by 58, let's just do it together so that you understand what I'm doing. If you have -256 and divided by 5, 5 goes there 52 times, -52 times. 5 goes here -52 times. -52 times 5, you get -60, 260. When you subtract this, it's the same as taking -56, then adding 260. What you get is 4x. So this would be 4x. What about 112? Negative. 5 goes how many times? So just take 112 and divide it by 5. It goes there 23 times. Negative 23 times. So 23 times 5, you get -115. And then subtract. You have -112 plus 115 gives you 3. So we found our quotient. What's the quotient? Yes, the quotient was this. This gave us 1x. This gave us 2. This one x squared. This gave us 3. It was 3x. And this one is the one we did earlier, later. Oh, it is here, in fact, it's just here. The quotient is here. Mod 5. The quotient is there, mod 5. And then the remainder is 4x plus 3. This is what I got here. So what I got as the quotient and the remainder. Now, this is the easiest way to do it. So the easiest way to do it is what I've already explained. Although there's another way you can do that, where you deal with it as Z as modified from the beginning. You did try that way to see that it gives the same result. So that when you are writing the code, you can see which one is easier for you to write. But when you are doing it manually, it's easier, first of all, to do it in Z of X, then reduce it, modify, and reduce the answer, mod 6. But if you're writing the code, it becomes easier, first of all, to change this mod 5. Change that to mod 5. So X square is already okay. It's mod 5. This one is negative. Make it mod 5 so that you are dealing with only positive values. Add 5 to it. You have X. Then this one, add 5 to it, you have 3. You turned this one mod 5. So the divisor is now in mod 5 form. And what about this dividend? Also make it mod 5. So for there, it would be x raised to 4. Just add 5. And then this is already okay, it's positive. 4x cubed is positive, so it's okay. But this is not positive. This is not positive, so you can make it positive. 3x squared. And then x is not there, 0, so then plus 4. Then we would ask ourselves, so we are now doing it mod 5. We've turned everything mod 5. And every time, anything we do, any result we get, we make it mod 5. As we progress, and you'll see we get the same answer. Now, so x squared goes here, x squared times. This x squared times the whole polynomial gives you x raised to 4, and that will be x cubed, and that will be 3x squared. Then subtract. I hope I've done it properly. So the multiplication is okay. So when you subtract the first, this one give us 0. This will give us 3. This will give us 3 x cubed. But this will give us 0. Then you, okay, so what about x squared inside here? It will be 3x. 3x, yes, 3x. It will be 3x. So this 3x times the entire thing will be x raised to 3. No, 3x squared. No, 3x cubed. 3x cubed. Then this times that will be 3x squared. Then this times that will give the 9x. Then again subtract. So this gives me 0, but this gives us 3, negative 3x squared. Of course, this is negative. We can make it positive. We can make it positive because we are dealing with the mod 5. So just add 5 to it, and you have a 2 here. Just add 5 to it, and you have a 2 there. So I hope you're getting what we are doing. It's 2x. You subtract. And this 9x from 0, you have negative 9x. Of course, you can make it positive by adding 5 to it, then 5, and you have a 1. I'm not saying it's bad to deal with these negatives. You can still deal with them and get the same answer. But we want to, every time we get it, we make it positive. We are working mod 5 throughout. We are working mod 5 throughout. Then then ask yourself, x squared into 2x squared, it will be twice. It will be twice. This 2 times the entire polynomial, you have 2x raised to 2. Then you have 2x. Yes, 2x. And then you have 6. You have 6. But 6 mod 5 is 1. 6 mod 5 is 1. So we are 1 mod 5 at every stage. 6 mod 5 is 1. So when you subtract, this first part is 0. This second part gives negative 1x. Negative 1x mod 5 will be 4. 4x. And this will be 3. So this is our remainder. This is our remainder, and this is our quotient. And those are the same results we got. Those are the same results we got because our quotient was that, which is the same, and our remainder of this, which is the same. But I said it's easier to work first of all in z of x, so that you're not worried about along the way. You're not worried that is it mod 5 or not. Just work out until you find the final result. Once you find the final result, now that final result, reduce it and you get the same result. When you are writing the code, I think it will be easier even to do using this second method. It will be easier to do using this second method here. Now, so you look at this example. I know we are recording the notes so that at your own time you can look at it and listen to how we moved doing it mod 5. And I want to do it mod 6. Want to do it mod 6. To look at the first strategy was that I will first of all do it as integers, the normal way. Then the final result, reduce it mod 6. So the final result that we have for the quotient is that, and the final result that we have for the remainder is here. So want first of all to get the quotient mod 6. So the quotient mod 6, negative 4 mod 6 is the same as 2. And you know what I've done? I've just added 6 to it. Was this a negative number? Add 6 to it. So in the normal thing, what we are doing is this. We are asking ourselves, 6 goes in negative 4, how many times? Goes in negative 1 times. Negative 1 times this gives you negative 6. When you subtract the lower one from the upper one, you have a 2. So that is what we are doing in the normal model arithmetic. That's what we are doing. But it's easier just to add 6 to it. You have that, of course, this 2. So, and again, this one, when you add the 6 to it twice, you have a 0 here. You have a 0 there. What about negative 58? Now, if it becomes bigger, it's easier to divide than adding. Then, and let me tell you how I'm doing it. Taking negative 58, I hope you have a calculator. So I'm just doing negative 58, and I'm dividing that by 6. And I can see on my calculator, it has written there negative 9.666. I don't take that, I take negative 10. When I divided, I got negative 9.66. So then if somebody was to ask me, how many times does negative 6 go into negative 58? I did with my calculator and got negative 9.66. What I write here is negative 10. I just add 1, subtract 1 from the result. I have negative 10. So negative 10 times that, oh, this was not negative. 6 here is positive. 6 is positive here. So I divided negative 58 by 6 and got negative 9.666. But somebody asked me, how many times does 6 go into negative 58? So then I say negative 10 times. So negative 10 times that gives me negative 60. When I see the results, I have 2. So again, this is 2. So this is our quotient. That is our quotient. What about our remainder? This is the remainder we had when we did normally. Now we reduce it mod 6. So we are doing it mod 6 now. I have negative 256. Negative 256. Negative 256 divided by 6. I get the fact when I do that with my calculator, what I get is negative 42.666. Negative 42. So what I write here, therefore, is negative 40. Not negative 40. I write negative 43. Negative 43 times 36. Negative 43 times 36 would give me negative 256. No, 50. Negative 258. When I subtract this, I get 2. I get it 2. So again, I've gotten 2x. What about 112? Negative 112, it's negative also. Divided by 6. You now understand what I'm doing. You now understand what I'm doing because that's what I'm explaining. Negative 112 divided by 6. My calculator says, this calculator says negative 18.66. Negative 18.66. So right here, negative 19. So negative 19 times 6 gives me negative 14. Subtract, I have a 2. So this is the remainder and this is the quotient. So how did I do this? I did it normally. Then the result, the end results are the ones I've reduced mod 6. The end results are the ones I've reduced mod 6. Otherwise, if you want, you can work with it mod 6 from the very beginning. Convert your divisor mod 6, convert your dividend mod 6, and then begin the division. And at every point, as you do the division, maintain your results mod 6 if you want. If you want. But you can do it without caring. Just do it normally, then reduce the answers mod 6. The way I've done that. So when you do that, this is what you get. This is what we've just gotten. Those are the results. Okay, I've our Rust code also for that. Okay, I forgot to include the polynomial so that you see how it's entered. I should have included it somewhere here. Should have included it here. I should have said that this is negative. Say this polynomial. It was this polynomial. But it's just the same thing as we did earlier. This polynomial, the first term is -4. So you see this is a constant. Then x raised to 1. No, I will interchange this. So this is 0. Then there's a 4 here. So this is the constant term. Then the one with x raised to 1, the one with x raised to -2, no, the one with x raised to 2, x raised to 3, then x raised to 4. So this polynomial is the same as x raised to 4, x raised to 4. Then there's an x raised to 3. And then there is x raised to 2. And then there is x raised to 1, there's nothing. Then there's a constant 4. So x raised to 1 is 0. And then this one also this is a constant. X raised to 1, then x raised to 2. So let's run this and see. So it gives us the same result. This is constant, then 2x. So it's 2x plus 2. This 2x plus 2. And this is the constant, x raised to 1, then x raised to 2. So this is 2x squared plus 2. So that is, so it gives you positive results. Gives you positive results. Otherwise, if you don't write properly, then it will be giving you negative results. It will be mixing positive and negative results. Okay, unless somebody has a question, any question? Okay, if there's no question, then Kwembur, welcome. Doctor, how are you?
Yeah, thank you very much. I followed a lot of good mathematics. Thank you very much for the lesson, and I enjoyed it. And to your students, I wish you all the best. Thank you.
Thank you. I wish to stop there if there's no question. Alex?
Yes, thank you, Dr. Tari. We resume tomorrow, same time. Thank you.